So for today's talk, we have Lalith Suresh comes to us from VMware Research. He's done a lot of work on managing various infrastructures, initially networks, and more recently clusters. And he'll be talking to us about the work he's doing for cluster scheduling, but he's also been doing some other interesting work for testing and understanding controllers in Kubernetes and other kind of cloud native clusters. With that, I'll hand it over to Lily.
All right, thanks for the introduction, Theo. It's also nice to see an actual hall with people in it, right? It's been a while since we've had this type of interaction, but yeah. So I'm Lalith from VMware Research. So I'll be talking about some work we've been doing on making it easier to build certain kinds of components in cluster managers. So no matter what you're running in your data centers, right? Whether we're talking about running containers or serverless functions or VMs or what have you, or Hadoop jobs, it doesn't really matter. The problems tend to be the same. And usually you'll find your data center has many layers of these things called cluster managers that are responsible for taking these workloads, assigning them to physical or virtual resources, and configuring the underlying infrastructure and applications to run in a certain way, right? And this is what these cluster managers do. And so a lot of my research has been focused lately on trying to make these cluster managers and the components in them easier to build, develop, and test, right? And in this talk, we're going to focus on some work that's looked at answering this question in the context of pieces of cluster managers that do these type of policy-based optimization tasks. So think of problems like scheduling, load balancing, workload migration, rebalancing, these type of tasks in the presence of some policies. And so I'm going to present a system we've built called DCM. It stands for Declarative Cluster Managers. And instead of the main idea here is that instead of having developers craft ad hoc heuristics over and over again to solve these type of similar, very hard problems in many different kinds of settings over and over again, we're going to suggest a very different way of going about it, where we're going to have the developers specify what they want their cluster manager to do and not how it should do it. And turns out once you have the separation, you have a lot of leeway on the how part. And here I'll show you some tricks using code generation and constraint solvers in order to take care of the how. All right, so this is a one slide, very high level summary of what I'm going to be talking about today. So let's get down into the details. So I'm going to take the example of the Kubernetes scheduler to sort of motivate this problem, right? And I want to remind you that neither the problem nor the solution is specific in any way to Kubernetes or its scheduler, but it's a pretty well-known example that we can use as a running example. So in Kubernetes, you have pods that you want to assign to nodes, and that's the scheduler's job. And so these pods come with all kinds of requirements, right? So the pods might have CPU, memory, disk requirements. It might have arbitrary made-up resources as well that it might request. Some of these pods might want to run in the same rack or the same geography. You might have anti-affinity constraints where they don't want to run near each other. Some of these constraints are hard constraints like the ones I mentioned here. They can also be soft constraints where you say like the pods need to be distributed evenly across different parts of your cluster or so on. But in total, you'll find that the Kubernetes scheduler has something like 30 different hard and soft constraints that it's supporting, and this seems to be a slowly growing list. And so the algorithmic problem that the scheduler is trying to solve is of taking all these pods and finding high quality assignments of these pods to nodes such that all these constraints, all the hard constraints are satisfied, and as many soft constraints as possible are satisfied. And this is
Can you take a question?
Oh yeah, sure. Go ahead.
So I'm confused by what you're saying here, because I would have thought the constraints are, I'm sorry, here's what I'm getting at. When you say do not place us on the same rack,
yeah,
that is a property of individual things that are running on top of Kubernetes and not a property of Kubernetes itself.
Yes.
Right?
Yeah.
Like I have a pair of things that I want to run on the same or not run on the same rack. Multi has the opposite constraints. So yes, those are constraints of the users of Kubernetes. So you say there are 30. I don't think you mean 30 hard and soft constraints. Maybe you mean 30 types of constraints?
Yes, so you can think of this as the Kubernetes scheduler supports many kinds of policies, and these pods can have some policies tacked onto them, right? So in this case, as you mentioned, the two blue pods might have in their specification something like I'm affine or anti-affine to pods that have a certain shape.
So I get all that. I'm just trying to figure out what the number 30 represents.
Oh, it's 30 types. So you're correct. Yeah, it's 30 types of constraints.
The policy language has 30 different possibilities, and you can mix and match and get those 30.
Exactly.
Thank you.
Yeah, cool.
I'm good.
Yeah. All right. So the algorithmic problem that the Kubernetes scheduler has to solve is like it has to ingest knowledge of all these pods. It has all these constraints configured on them, and it has to satisfy all of it. It's a well-known NP-hard problem. So there are no silver bullets here, right? But if you look at how people go about implementing systems like the Kubernetes scheduler today, you'll find that it's actually implemented as a collection of these best effort heuristics that have to be chained together in a certain way in order to find these assignments of pods to nodes. And you'll typically find that it's different heuristics to evaluate different kinds of constraints. So to give you a bit more of a precise view of how this looks like, the most popular approach to this seems to be to do what's called a filter score design. So in Kubernetes, the first thing that the scheduler will do when it sees this, when you have a new pod, is to go through what's called initial placement. And in the filter score approach, what you have is you can imagine that there's this priority queue of pods. How they prioritize isn't important. And then the scheduler also keeps a list of the current nodes. And now the goal is to figure out which of these nodes are we allowed to assign these pods to. Okay. And so the first thing that the scheduler will do is that it'll take this pod, it'll take one of the nodes, and then it'll go through the filter pass, where it's evaluating for, like it's evaluating different kinds of constraints. And it's making a call looking at this pod and this node, whether any of these constraints are satisfied, right? So each of these filter heuristics basically outputs true or false. And if all of these constraints are true, then we can go to the scoring pass, which is again similar. You evaluate a bunch of scoring functions again for the pod and the node. And this typically represents things like your soft constraints. And at the end of the scoring pass, you for each evaluation of the scoring pass assigns us, an integer value to the pod, integer value to the node, and then you sum up all the scores, and you basically get something like this, right? Like, so the yellow node has a score of 40, and so now you have to. Sorry, go ahead.
Is it important to understand what's on the screen, or is it going to be superseded and we don't have to understand it too well?
Not too well.
Okay, then I'll pass that.
Yeah, but you should ask anyway. We have time. Yeah.
No, it's good. It's good. We can come back to it later.
Yeah. All right. So, okay. I'm somehow having a trouble registering clicks with the Zoom. Anyway, so now the scheduler needs to actually repeat this process for every node for this blue pod, right? And so some of them will survive the filtering pass, some of them won't. But at the end of the day, you basically end up with something like this, right? Let's say 2 of these nodes survived the filtering pass and then was assigned a score. And then you assign the pod to the highest scored node, right? And that's where the pod ends up. So let's look at a few properties of this design, right? Like this filter score design. So the first thing is that each of these policies is usually implemented as a heuristic. And sorry, I'm having some trouble with registering clicks on the Zoom. Yeah, so each of these policies is typically implemented as a heuristic. And it works well when you're only looking at these type of local properties where you just look at some properties of the pod and the node and you decide yes or no, or you assign a score. But this starts to get hard when you run into these constraints that require you to reason globally about groups of pods and groups of nodes, right? So the classical example here is the one we mentioned earlier, which is interpod anti-affinity, right? So how would you design this? How would you implement such a policy in this architecture? You would basically need to craft this heuristic in a way that you make local decisions that are somehow consistent with this global property you're trying to preserve. And the way you end up doing that is the piece of code that's implementing this particular heuristic maintains a bunch of in-memory data structures that remember information about, say, currently active groups of pods that have to have this property maintained, right? So you might end up something like you have a data structure that says on the rack dimension, these are groups of pods that have interpod at the MQTTs active. And so you make a decision for the blue pod now, and the next time you see the green pod, you again look up this data structure to know, okay, now this is a node I'm not allowed to place pods on, right?
So I can just ask a somewhat pedagogical question, because I suspect not everybody in the audience is familiar with cluster managers. So there's an implied assumption here that you want to get to an optimal solution, right? Because all this stuff about data structures and caching optimizations only matters if you actually want to get to the optimal solution. Otherwise, you can just throw the blue pod in on some machine, right, and then throw the green pod not on that machine, right? That machine now no longer satisfies the green pod's hard constraint, that it can't be on the same machine as the blue pod, so you've just reduced the set of machines that the green pod can be on, right? But the problem with that is that you can box yourself in a corner. If you want an optimal solution, then you have to do this, pre-computing data structures, figuring out exactly what your options are, and then pick the best one, right? Is that correct?
I think even knowing which node you're not, this is all, I'm just discussing feasibility at this point, right? Like this is only to find out even which node you're not allowed to go to. So you need those data structures in order to make evaluation of that thing efficient.
Evaluate this jointly for two pods. I can just assign the blue pod, and then when the queue gets to the green pod, then the machine that I put the blue pod onto is no longer feasible, right?
Yeah, but the way this, so how do you so in this design, when you have the green pod, you need to actually look at the set of node, so you're going to make a call on, say, you need to pick a node to put the green pod on, right? Are you suggesting that you pick one at random and then check whether the blue pod is there, or?
It's going to be a simple data structure that just keeps track of the current assignment, right?
Yeah.
You need to keep track of the assignment anyway. That's the point of a cluster scheduler, right? That you keep track of the assignment. So but I think Lalith, what you're saying is what I mean. That you simply, if the blue pod is there, then there's that machine does not pass the feasibility check for
exactly.
Right. So basically, it's another heuristic in your list of H heuristics that says, is the blue pod there? If yes, then don't go there. If no, then it's feasible.
Yeah. Right. So another way to frame this question is, imagine each of these nodes has hundreds and hundreds of pods on them, right? So you're going to run this filter score pass where you're basically checking for the green pod, you're going to have to evaluate every node. So you don't want to scan the entire list of pods on every node in order to determine whether you're allowed to go to that node or not. So they're trying to make it a bit more efficient than that, right? So you have some data structures that let you look up very quickly whether the green pod can go to a node. That's what I was describing just now. Yeah.
Can I ask one more sort of maybe slightly pedantic question? If you're running out of time.
Yes, keep it coming. This is good.
You went from talking about individual nodes, individual pods, to global reasoning. But the constraints shown us so far are non-local, which is different from global.
Fair enough. This is somewhat much more easier than other kinds of global constraints. But what I want to convey is that it already gets hard at this point.
I'm curious because you haven't shown us the sort of expressive power of your constraint language. Do you have truly global constraints?
Yes. I'll show you later. Yeah.
Oh, okay, good. Go ahead. Then. Keep going.
Yeah. But this is still the baseline. So it's a bit of a slow ramp to before I describe our solution. Yeah.
In the literature, this is often referred to as a combinatorial constraint.
Yeah. Exactly.
Optimizations here are not on the solution, it's on the controller implementation.
Yeah.
Was there a question at the end? I couldn't hear you properly. Sorry.
There's a question in the form of a comment. Keep going.
Okay. All right. And so, with some effort, you can actually design those data structures well. But now what happens if we try to tweak the constraint a little bit, right? The requirements evolve. You want to tweak the policy a bit from not saying, let's say, you want to evolve the policy from the Boolean variant, which is, no two pods of this type should be on the same node, to, let's say, I don't want more than 3 of the same type to be on a node, right? So once you get to this place, a lot of those data structures that I mentioned earlier have to be redone. And this exact process happened in the context of the Kubernetes scheduler, by the way, which is why I'm picking this particular example. Right? So the optimizations that you prepare, like these data structures and lookup tables that you prepare, have to be adapted each time requirements or the kinds of policies that you want to support evolve. And this gets hard the longer you're doing this. All right. Okay. And so there's also another question here, which is how do you keep all of this performant, right? So people do different kinds of things. Some systems sample, like you don't consider all the nodes in your cluster every time you want to place a pod, you consider some subset. If you don't sample correctly, you might actually miss feasible solutions, right? And given that each of these policies are of different difficulty to evaluate, you can actually order them in a certain way so that hopefully pods get filtered out early and you're not evaluating the more expensive constraints. So this is the kind of thing that the Kubernetes scheduler does to keep performance sane enough, right? So that you can run this at scale. And you can do all of this. You can design a very good initial placement system, but you've still only solved initial placement, right? So this is still the question of, which is the first node I assign a pod to? And now what if that doesn't succeed, right? So in Kubernetes, you fall back to what's called preemption, where you're going to make room by removing some lower priority pods. And so again, you have a few more heuristics in here to basically pick potential nodes to consider to kick pods from. And then there's this dance that they do where they select some pods to remove, and then they reattempt this placement, assuming that those pods are no longer there, and see if it succeeds. And if so, they'll place the higher priority pod on that node, right? So there's a few more heuristics that show up. But now that's just, the question of deciding how to place one pod at a time. It turns out there are problems where you actually have to reason about groups of pods at a time, so-called gang scheduling, which has come up, right? So in Kubernetes, there's an entirely separate project called Volcano, which does nothing but gang scheduling and a few more sort of batch scheduling kind of policies, right? So they have an entirely separate code base just to do batch scheduling, but really the problems are kind of similar. And then there's this thing called descheduling, which is you're not actually placing any new pods. You just want to remove existing pods according to some, according to some rules, right? Like this is usually to reap some capacity from the cluster by removing pods that have been running for too long and aren't really of high priority or something like this. But all four of these problems are very similar in nature, right? They're all combinatorial optimization problems where you're trying to assign or remove pods to nodes according to some rules. In initial placement, you're only allowed to assign pods. In preemption, you're also allowed to kick out pods. Batch scheduling is the same as the above, except you're doing it for groups of pods at a time. And in descheduling, you're not allowed to assign pods, you're only allowed to remove pods, right? But you end up having too many different code bases to solve basically the same problem with slightly different flavors. And this is just Kubernetes, right? This is just like a very tiny slice of the kind of scheduling problem that appears in a modern data center, right? And so we've looked at many sort of open source and commercial systems in the space, and it's always the same story, right? Like you have the same kinds of optimization tasks that show up. Everyone's reinventing their own heuristics. These are the same problems. It's a lot of code. It's hard to maintain and so on. And usually we find that there are these problems like scalability shows up all the time, especially as the kinds of constraints you want to support get more complicated. There's always this question of decision quality, right? Like how good are the decisions that your cluster manager is making? And Malte brought up optimality rate earlier on, but the problem is that forget optimality, these things sometimes even miss feasible solutions when they exist, right? So optimality, I think, is a very, very ambitious goal already, given these designs. And the bigger problem that motivates all of this is extensibility, right? Adding new policies, even simple policy level feature additions can take an unreasonably long amount of time. And adding new features sometimes end up having you to redesign your cluster manager a lot, right? And these are the main problems that we're interested in tackling. So with that, I'll present our solution. It's called DCM, it stands for Declarative Cluster Managers. And so to build the same kind of scheduler with DCM, what you would do is so the first thing we ask developers to do is to represent the state that the cluster manager is looking at in a relational database, right? So now you have a schema representing your pods, your nodes, and all your other all the other information that's relevant for something like scheduling. Now, this doesn't need to be like a full-fledged database like MySQL or Postgres. It can literally just be an in-memory embedded database, right? We just need a relational way to sort of reference them. And now against the state, we're going to describe our policies as constraints in SQL. And I'll show you how that looks like in a moment, but we basically write SQL queries that describe the hard and soft constraints that we'd like to preserve against this cluster state. Now, it turns out that once you have this declarative specification of the cluster state and the policies you want to enforce on them, it's enough information for a compiler to generate a blob of code that can replace a lot like the kinds of heuristics that I've been describing so far. And in particular, what happens at runtime is that when you invoke this generated code, it pulls in the latest state from the database, it efficiently encodes that into an optimization problem, and it uses a fairly good off-the-shelf constraint solver to solve it under the covers, and we can wire the results back. So basically, at the end of invoking this generated code, you get your assignments of pods to nodes, for example, right? And so this is the high-level overview of how DCM works. A quick teaser on some results. We've basically, again, evaluated it along these three axes: scalability, decision quality, and extensibility. And we've applied it to several use cases. This list has actually gone, it's a bit longer than it was when I made these slides a while ago. But these are fairly different use cases, right? So one is a Kubernetes scheduler, the other is a VM load balancing utility in the context of a commercial cluster manager. And the other is like the sort of control plane within a distributed database. So these are three different use cases. We've applied DCM across all of them. And for scalability, we've found that, for example, in end-to-end measurements against a Kubernetes scheduler, on a 500 node scale, which is fairly modest, but it's still pretty big in most enterprises, we can actually beat the very heavily hand-optimized Kubernetes scheduler with respect to the time it takes to bring up a pod, right? So on the 95th percentile, we're up to 2 times faster. And it's worth emphasizing that the default scheduler is sampling. It's only looking at half the nodes, whereas DCM is looking at all the nodes. So if you make the default scheduler look at all the nodes, it becomes 4x. And since the paper at OSDI last year, DCM has become 3 times faster. So we're now going to run some more experiments to compare it against the default scheduler again. For decision quality, by virtue of using a constraint solver under the covers, we basically find that this translates into things like better decisions, which mean things like better load balancing, faster preemption, or even finding solutions at all, especially in scenarios where you have fairly tightly constrained packings going on. And for extensibility, we found that typically adding new policies in a system built using DCM is a matter of, say, adding this 20 lines of SQL roughly. And even extending an existing code base with fairly non-trivial features becomes quite possible. For example, we took our Kubernetes scheduler and we made it sort of reason in a unified way about pods and VMs at the same time in the context of a commercial Kubernetes distribution that also supports VMs. Right? And doing this in the with the baseline Kubernetes scheduler would have required you to sort of rewrite everything pretty much. But with DCM, it was just a matter of adding some small changes to the schema, right? Like you add a column that says whether a task is a pod or a VM, and then you add some constraints that's specific to VMs, but not pods, and the other way around, right? And then it just works, right? So any questions before I go into the programming model?
Oh, now we're excited.
Okay, cool. All right. So like I said, the first thing you're going to do when you're working with DCM is to design a schema to represent your cluster state, right? So this is exactly what you would expect. Like, so in a Kubernetes scheduler, you would have tables of pods, tables of nodes. Pods have to be assigned to nodes. So you'll have a node column in the pod table. There's a foreign key relationship, all the standard SQL 101 stuff, right? But now, because we want DCM to figure out the assignment of pods to nodes for us, we're going to annotate the nodes column as a variable column, right? And so what this tells DCM is that the cells in this column can draw values from the node column here, and it has 3 different options and it knows that because of the foreign key relationship, right? So now DCM knows, okay, I'm going to have to assign values based on this other column. And with just this, of course, it's not a very useful thing because DCM will just, assign everything to the same node and say, yeah, job's done. But if you want to make this abstract, like this mechanism useful, you need to bound it with constraints, right? So DCM supports both hard and soft constraints. To write a hard constraint, you write some DDL in SQL like this. You give it a name, you say, create constraint. And then every constraint has the same shape. You select some rows and then you specify some predicate that should hold true for every one of these rows, right? So a very simple kind of constraint would be to say, I don't want pods to be assigned to nodes that report to be under memory overload. So to do this, you would say something like select star from pods and check. This means it's a hard constraint that pods.node, which is your variable column, is in some set. And the set again can be specified using a subquery that says, give me all the nodes that are not under memory overload. So this is a simple example. In practice, things look a bit more complicated, and I'll show you all the different constructs you can use in 2 slides.
Lalith, can I ask a quick question anyway?
Yes. Yeah, go ahead. Yeah.
I'm trying to understand how you're going to model the rich complexity of data in the world. You've given us one example here where you sort of take something else is responsible for figuring out what overload means.
Yeah.
And it gets reflected in the SQL table as just like a Boolean or some very simple SQL data type. And then you write the constraint over the SQL data type, but then something else is responsible outside for determining how to populate this table and what all these words mean.
Yes.
Is that a general pattern we're going to see, or is this like not what actually happens?
In practice, all of this looks a bit more complicated, but this exact thing actually is there in the Kubernetes scheduler we built because we get this memory overload thing directly from the Kubernetes API.
Got it. Okay,
right?
Thank you.
But you can also, I'll show you exactly what it, I'll show you all the constructs that show up. Yeah. Similarly, you can also do soft constraints where you select some rows, but now you provide an expression whose value you want to maximize. And you can use this again in, was there a question?
You're good.
No, okay. And so one way to use this is to say something like, you compute a join between 2 tables, one of which has the capacity of the nodes, the other is again the pod table. And then you compute some aggregate that gives you the spare memory capacity per node. Now note that this itself is a variable because the value of the spare memory capacity here depends on the assignment of pods to nodes to begin with, but you don't have to worry about that. DCM will take care of sort of generating intermediate variables, linking them, all of that stuff, right? But then once you specify such a view, you can then say, I want to maximize the minimum spare capacity on this column, which basically forces these pods to be spread across nodes. But in general, the programming model is like this, where you express policies somewhat concisely using SQL queries, and you have a lot of the power of SQL at your disposal. You can use joins to cross-reference state across many different tables and views that you compute. You can use aggregates, you can use group bys, subqueries, correlated subqueries, you can use arrays. You have a lot of expressive power here. I don't know if that answers the question I got earlier about.
Yeah. I wanted to follow up on, I guess, Sriram's questions. Some of these tables that you showed on the previous slide, right? These are views that you define because you find them useful in your policies, right?
Yes.
So there is this max available capacity thing that you had, and those are not, per se things that have to already exist in Kubernetes, right? You can also
Exactly.
use yourself tables and views that you can then conveniently join against, aggregate over,
Exactly.
etc.
Exactly. So this actually touches on a fairly important point in that often what happens is that these, like if you look at, say, the Kubernetes scheduler, there is some base information that it gets from the API, and then it has to actually compute some things on its own. For example, the one thing that I'm a bit surprised always that the Kubernetes API doesn't tell you is the spare capacity per node. You kind of have to compute a join between the set of pods and nodes in order to and an aggregate in order to get that. So that's the kind of thing that we can compute at our end if we need to, but we can also get things raw from Kubernetes if needed, right? Yeah. And so more concretely, the programming model looks like this, right? This is written in Java. You instantiate these little models that represent the specific kind of problem you're trying to solve. A model is parameterized by a connection to the database from which we get things like the schema, and then a list of constraints one string per constraint that represents the kind of SQL that I showed you before. And once you invoke this, behind the scenes, there's a compiler, it generates some code, it compiles it, it loads it into memory, it wraps it in this model object, and it gives it back to you. And every time you call model.solve, what happens is we pull in all the tables that the model needs, and out comes the same tables, but with values assigned to variable columns, right? And then you can basically walk this table at the sort of client side in order to decide, okay, this pod has to go to this node. I'll issue some external API call to get that through.
Presumably, there's also some sort of model.incremental solve and things like that.
We'll get to that in a moment. Yeah, so this is a very good question. We'll get to that in maybe 2 slides.
No problem.
Yeah, so the programming model is basically tables in, tables out, with values getting assigned to variable columns. And of course, sometimes you cannot assign values because you've given it an unsatisfied problem, in which case you basically get back. We use this capability we use this capability that solvers usually provide in giving you back what's called an unsatisfiable core. Right? So you get an exception and it'll tell you which constraints were unsatisfied. And we are also trying to augment this currently with the exact rows from which tables were also part of the unsatisfiability criterion. So you can actually get a very small explanation for why things weren't solvable. And this is quite handy when you're debugging, pretty much. Okay. So what ends up happening once you have this programming model is that you end up instantiating different models to represent different kinds of cluster management tasks that operate at different time scales. So one way we've used this, for example, is to have an initial placement model that only looks at the set of pending pods and summaries of how they relate to existing pods and nodes, and use that information to only try and place the current set of pending pods. And if that doesn't work, we can fall back to preemption, where we sort of zoom out a bit, look at a wider range of pods and nodes, and decide which of them we can preempt potentially. And descheduling is pretty much the same as preemption, except you're not allowed to assign anything new.
Lalith, can I ask a quick question?
Yes.
Maybe it's where you're going, but I feel a little confused because I feel like I've heard about 3 different languages here. One is the language of SQL. Another is you mentioned unsigned cores from SAT. And the third one you mentioned, is you sort of talked about combinatorial optimization, which is more like numeric constraints. And I'm trying to figure out like what is actually running under the hood.
Under the hood, we'll get to that in a moment. It's basically like we represent it as CP.
Just go on then. It's fine. It's fine.
Yeah.
I'll wait.
Yeah, we represent it as using a CP solver. I'll get to that. Yeah.
Okay.
Right. So what ends up happening here in this model is that you can actually use the database for all its strings. Right. So for initial placement, for example, you can filter on as like any irrelevant information. Just keep it in the database. Don't even bother don't bother DCM or its constraint solver with any of it. For example, you don't need to like someone brought up incremental placement, right? So here you don't need to actually look at all the existing pods. You can actually compute some summaries of how the pending pods relate to them and only bring that information in, right? So you can filter out as much of as you need early on in the database. If you already know that you want pods to end up closer to some nodes over others, you can compute that directly in the database, give some kind of ranking, and basically express that as a soft constraint that the model should preserve, right? So if you know of any preferences that you don't really need the solver's capability to deal with, compute that in the database and just give that as a preference to the model. You can also compute various kinds of expensive aggregates, like this thing we mentioned about the spare capacity per node is a classical example, but we can also use this to compute, say, the groups of pods that are mutually affine or anti-affine, and ask the solver to always respect that when it's making placement decisions. And once you compute all of these aggregates and summaries from the database, you basically have hard and soft constraints that consume these as views, basically, right? So these are, from the model's point of view, tables and views are the same. It just needs to be able to query it and get some records. You can basically compute whatever you want in advance in the database if you think it'll simplify life on the DCM side, right? And so to the question about incremental placement, you kind of have to craft your model in a way that it becomes incremental, right? So you kind of look at only the new changes that you want to make decisions for, right? And if you don't need incremental placement, you basically can sort of look at the entire set of pods if you want to, right? But how you scope so you kind of have to make a judgment call of how you want to scope the problem given the sort of performance point you want to be at, right? So if you want to make fast incremental placement decisions, you only look at a smaller subset of the database and pre-compute as much of the problem as you can in the database. Does that answer your question?
Not fully, Lalith. I mean, it does answer my question at a level, but I feel like you're basically saying I have to have crafted two versions of my policies, one that was designed for like the no prior solution and the other that was crafted for prior solution. There's a fair bit of good work over the years on incrementalization of solutions, where you write as if you're not incremental, but then you incrementalize, you produce the version that says, here's how we're going to update things, right?
Yeah.
Maybe that's a future work for you or something, I don't know.
It comes up often, so we've not yet had a good reason to do it that way. We've not had to write two sets of policies, for example.
I'm surprised to hear you say that. I would have thought you're always in the incremental mode, right? There's a working cluster. A new job comes. I need to figure out where to hit it. I need to take something off. That's a kind of incremental change.
Exactly.
Yeah. Always incremental. When are you ever not?
Yeah. So as you said, that first sentence you mentioned is on point. Like it always looks like an incremental problem. It's just that what part of it are you going to consider as variables changes a little bit, right? Okay. So for preemption and initial placement, so we've actually written the Kubernetes scheduler in a way where we say there's a group of fixed pod and there's a group of unfixed pods, right? It's just that these two groups look a little different for these two problems. And we can decide that when we query from the database, right? But the constraints are the same, right? I think in preemption, we add one more policy to consider, but like the way the policies are written, there aren't two complete sets of policies.
There's something going on in your solver where it tries to produce a minimal difference from a previous solution, because you don't want to take a job from here and move it there just because you picked a new solution.
Yeah. So the solver has no memory of prior invocations. And that was a conscious design decision because in practice, the solver, like this code is not the only thing changing the cluster, right? Yeah. So it's stateless.
And an operator might come in and do something, et cetera, et cetera. Yeah. Okay.
So there is actually so we've actually thought of doing what's called, so in MIP solvers, they call warm starts. Where you say, like, you give it a hint and say, okay, like, try to find a solution as close as possible to this, right? So you could possibly play with that, but we've never had a need for it yet. Yeah.
But what you will need, of course, to do is avoid the kind of disruption that Sriram mentioned, right? Where, because of some tiny difference in an optimality score, the solver decides to like shuffle around the entire workload in the cluster, right? That sort of thing happen, and I'm curious how you solve it. I'm sure
unless you have the cost of migration, that's another way to solve it.
Right. So if you model
here's the cost of migration, and then maybe it makes sense. Yeah.
If you have a maximum disruption budget.
Yeah. So the scoping offsets that concern a lot, Malta. Like by only looking at the pods you want to place, right? And if you're actually considering a large group of pods, for example, in preemption, you actually have to prevent unnecessary preemptions by using things like the pod disruption budget and things like that. Right. Yeah.
Right. So the second part of your statement, I agree with. The first part, I don't agree without further information, because if you just look at 5 pods that you want to place, you can end up with sort of a very unfortunate cascade effect, right? Where to place those 5 pods, you move 5 other pods to move those 5 other pods that you preempted and rescheduled somewhere else. You need to move another 5 pods, and then you, at the end of the day, shifted your entire workload.
So you mean across placement decisions you're making? So let's say you place only 5 now, and next time you do preemption, you kick out, like you move others. Like, is that the kind of effect you're talking about?
I think I understand why this is a problem for you, because placement and preemption are actually 2 different models. They happen at the same time.
Exactly. Yeah.
Placement, consider the option of preempting in order to make room and then immediately place something.
Yeah.
right?
Yeah.
So you need to first run the preemption and then reconsider your placement. But that does mean that when you run placement, you're not going to consider solutions that involve preemption and moving things around.
Yeah, exactly. So if that was important, you probably only run a model that always also reasons about preemption. But in Kubernetes, this is usually not a big problem. Most of the time, you want to succeed on initial placement, right? So, all right. So I'm going to go quickly over the internals because it's come up a few times already. I also want to be a bit cognizant of time. So we have 20 minutes, and I think I should not need more than 10 to 15 for the rest. All right. Okay. So behind the scenes, what happens is we get we have a compiler that basically looks at the schema and the constraints. And from this, we need to generate some code that you can actually run at runtime, right? So your schema and constraints are basically some SQL queries and some DDL statements that give you basically type information of different columns. And there's a bit of a process to this. This is very standard compiler stuff, right? Like, so there isn't much interesting going on here. But ultimately, what ends up happening is that we need to wait, I think my slides are stuck again. Yeah. We need to generate code that's specific to the kind of solver that we're using. So we support two different kinds of solver backends. One is MiniZync, which is the first solver backend we worked with. And MiniZync is basically something that gives you a very high level modeling language for working with different kinds of constraint solvers. So you write one kind of model and they can compile that down into different kinds of solver backends, but that's just really slow. Like you can't scale the system beyond, say, 20, 30 nodes with MiniZync. So we then switch to generating code that works with Google's OR tools toolkit. In particular, they have a CP-SAT solver, which is what I'll describe in a moment. Okay. And so the kind of generated code that we would produce looks something like this. So if you have a constraint which specifies, so if you have a constraint like this, where there's some join and you're specifying this expression as a constraint over every record here, what would you need to do? You would need to pull in all the records corresponding to T1. Then you iterate over these tables, you generate a for loop. A join can be done with some kind of index. And a where clause is basically an if statement that sort of filters out irrelevant rows. And the constraint itself, for the constraint itself, you basically use the APIs given to you by the solver and all the formalisms that it entails in order to encode basically the inputs into some kind of constraint that you then pass to the solver, right? So of course, you kind of have to generate very good Java code here. You don't want to make unnecessary passes over the same data, blah, blah, blah. But the most important bit to get right is basically how you interact with the solver itself, right? And this is the key technical challenge that we've had to solve in DCM, which is how do you wield these constraint solvers effectively? So I'll give you a little bit of an overview for how solvers like Google's CP-SAT solver works. So the CP-SAT solver is based on the technology described in this talk.
Are you using Ceres? Which solver are you using?
It's called the CP-SAT solver in the Google OR tools toolkit. Yeah.
Google has several solvers. Why am I not shocked? Okay.
Yeah. And so this is if you're interested in this subject, you should check this out. This is the talk. It's called Those Who Cannot Remember the Past Are Condemned to Repeat It. It's a talk at CP 2013. And this is considered quite a breakthrough in how CP solvers are built, and it makes them ridiculously fast. And it turns out for the kinds of problems that we're presenting to the CP-SAT solver in the context of, the kinds of cluster management tasks that we've been seeing, the solver is hardly breaking a sweat. And this is what's making this system even feasible, right? And so what is CP? CP just stands for constraint programming, where you're describing these optimization problems as using some variables and fairly broad kinds of constraints, right? And the whole spiel behind the CP-SAT solver is making CP very efficient by also augmenting it with the SAT solver. I won't go into how the CP-SAT part works, but I'll give you a bit of a crash course on how CP itself works. So in CP, you have variables. So let's say we have V1, V2, and let's say we have a a range of values that V1 or V2 can take. This is called the domain, right? So in this case, V1 can take values 5, 6, or 7. V2 can take values 6 or 8. And now you have constraints. So let's say I have a constraint that V1 should not be equal to V2. So CP solvers typically back each constraint by an object called a propagator, a constraint propagator. And the propagator's job is to propagate changes in the domain of any one of the variables it is linked to the other variables that it is linked to. So as an example, if during search, let's say the solver decides it's going to fix the value of V1 to say 6, it can then the propagator knows, the not equals propagator knows how to then propagate that change to V2, in that it'll actually remove 6 from V2's domain, and that sort of shrinks V2 domain, right? And then now, because V1 and V2 only have one entry in their domain, that's a solution, right? So search basically progresses. So the solver basically progresses using a mix of search and propagation, where changes in the domain of one variable trigger propagation, and then that changes more variables, which triggers more rounds of propagation, and eventually you hit a fixed point, right? And that's when you have a solution. And so the input to any CP solver is basically a graph of your constraints and your variables. And this is what we call the encoding. And so, of course, in order to make the solver work well, you really have to be careful with the number of variables and constraints that you introduce. And in particular, in order to encode the kinds of problems that we've been seeing so far, you usually have to generate a bunch of intermediate variables and constraints. And you kind of want to bound their number. And so the compiler looks at the schema and the constraints, and it has some optimization passes. There's nothing fancy here, all the usual stuff you'll find in any compiler, right? Like you do some constant propagation, you do some sub-expression elimination, you leverage algebraic identities in the generated code. But the most important thing that we can do in all of this is to leverage what's known as a global constraint, right? So what are global constraints? These are constraints that operate on groups of variables, for which solvers usually implement specialized propagation algorithms. And the most classical example of a global constraint in a CP solver is the so-called all different constraint. Let's say you have 4 variables that you want to assign different values to. And usually problems where you're, let's say, trying to, like anti-affinities is one example, which eventually gets compiled down into this kind of formulation, where you have 4 variables that might represent the assignment of, say, a pod to a node, and you want them all to take different values. So you could either, in the encoding, generate a quadratic number of constraints, right? Like, so you say V1 should not be equal to V2, V3, V4, V2 shouldn't be equal to V3, V4, and V3 should not be equal to V4, right? Or you can just write this expression, right? You basically say this is an all different, and you give it an array of variables, and then the solver knows immediately what you're trying to achieve here, and it can use a fairly specialized set of propagation algorithms only to adjust the domain of these 4 variables according to this constraint. And so there are many kinds of global constraints. Usually there's actually there's a list of all possible global constraints that have been studied so far in a website, and like not all solvers support all of them, obviously. The OR tools solver has a couple. It also has global constraints that are very good for scheduling tasks, which we talk more about in the paper, but I won't be going in here for now. But the encoding basically determines the performance. Oh, is there a question? Sorry.
Not in the room, I don't think.
Okay, sorry. So the encoding basically determines how well your solver will perform for the tasks you're giving it. And so, like I said, we reduce the number of introduced variables and constraints, and we try to leverage global constraints where possible. And these are necessary because, so here's a benchmark task that we describe in the paper, which just tries to assign 50 tasks to 1,000 workers. And a fairly naive sort of literal translation of the SQL queries into constraints basically gives you something that takes 25 seconds to solve, which is completely useless. Nobody would want to go anywhere near this. But once you basically start using all the tricks I've described so far, you can actually bring this down to 16 milliseconds, which makes it very practical to run at scale, right? And this, you can do this with one thread. It's not even that hard to do once you basically can express these problems in terms of things like global constraints. Right. So some lessons learned during this process is that so we've basically had about 2 years of experience applying DCM to different use cases, not just the Kubernetes scheduler, which I've been expressing a lot so far. But most of the time, we're actually trying to understand the semantics of the use case, not writing SQL, right? So in the Kubernetes context, like I've spent most of my time basically looking at this mountain of Go code to understand what exactly they're trying to achieve. But once you figure that out and figure out all their corner cases and semantics, writing it out in SQL is not that hard. For performance engineering, most of the time is spent on the computations we're doing in the database side, right? Like the views we're computing, the aggregates and so on. And we're currently basically prototyping something where we're using an in-house incremental view maintenance engine to do that, right? Because a lot of these, like cluster management tends to be quite incremental in nature. So most of the time there's only a few things changing. So it really doesn't make sense to compute these very expensive cross products and joins every time a small change happens, because most of the work is being duplicated. And this is a very good case for incremental view maintenance. And lastly, like making use of unsat cores was quite useful during development, because when you're adding new policies, you're tempted to assume that maybe the policy you wrote is wrong, but turns out that in many cases, the new policy might have tightened the problem, which in turn violates some other constraint, right? So having that kind of feedback helps when you're using such a tool. So any questions before I quickly go into some graphs?
No, go ahead.
We're good. We're good.
Oh, okay.
We're not sorry, as you can.
I'll only describe like one of the results on the scalability end, which is usually the biggest concern when you're using something like a constraint solver. And so here I'll describe the 500 node Kubernetes cluster experiment where we deploy a series of applications in an open loop. And the characteristics of these applications, in particular, their resource demands and the number of replicas in a group, are drawn from this trace that we have from Azure. Was there a question?
Yeah, can I ask you a question? Like, I don't care about graphs. Like, are you actually using this in production?
Not yet. So there have been some trials going on, but no one actually runs this in production yet. But I'm working hard on it.
Why though?
So it has less to do with DCM than the fact that people who are running some of these systems, let's say, I don't know, internally at VMware, there's a thing called DRS, there's the Kubernetes scheduler. People have spent 10 to 15 years of engineering on all of this, and it's a tall order to ask them to rewrite everything using a new tool, right? So most of the places where something like DCM is interesting is if you're actually trying to build something new from scratch. And here, basically, again, this is where we have some trials going on, but none of these things are in production yet.
That makes sense. Thank you.
Yeah,
Thank you.
yeah. I'm also talking right now with some hyperscalers who are quite interested in, again, because they all have custom scheduling needs. They've been struggling to extend existing code bases like the Kubernetes scheduler, and they're also interested in DCM for this reason. But we have some scalability things to show first. Yeah.
Sounds like the strategy you need is to first invent constraints they can't solve, file a bunch of bug reports asking for the constraints, or show up and say, by the way, I coded them up yesterday afternoon since you didn't get back to me. So like, I just letting you know.
I think Lalith doesn't need to invent those constraints. They're already.
Yeah. Okay,
yeah, they already exist. Yeah. So a lot of the motivation for DCM, like in order for us to be sure that this is a real problem, we've been like, there are a lot of GitHub issues we've been perusing where it looks fairly straightforward constraint wise, but it turns out once you have to implement this as a mountain of Go code, it's quite hard, right? Yeah. So just one quick graph, and then I'll stop. So this is an experiment where we basically compare head to head with the Kubernetes scheduler, and you have 3 graphs here. They're all CDFs. On the x-axis, you have the end-to-end latency to bring up the pods. Y-axis, you have the fraction of placements that were under a certain latency. And you have these 3 graphs where we have on 0, like none of these apps are configured with anti-affinities. Then you have half of them configured with anti-affinities, and then you have all of them. And this is the mode where you want to be running. And people usually want to run in this mode in order to have fault tolerance, right? You don't want one node failure to take down more than one of your processes. And so when there are no constraints at all being configured, this is sort of easy mode for the baseline, which is, and here you basically see a slight advantage for the baseline scheduler. And again, keep in mind that the baseline scheduler is only looking at half the nodes it's sampling, right? So there's a bit of a price to using an off-the-shelf database and an off-the-shelf solver. There's some unnecessary constants, like constant overheads that we pay, and that shows end to end. But as soon as you start adding constraints, you basically see that DCM kind of stays very stable. There's a minor additional cost in getting more data from the database, but the solver is hardly phased. And it turns out these propagation-based CP solvers are very good at these type of tasks, right? These anti-affinity kind of problems and so on. And in the end, DCM cuts down the 95th percentile latency in half compared to the baseline scheduler that just keeps getting slower the more harder a problem you present to it. And so there's more details in our OSDI 2020 paper, including experiments of up to 10,000 nodes. There's more internals about how the compiler works and so on. But that's it. That's all I have. So I've told you how certain kinds of optimization tasks are a recurring problem in any kind of cluster manager. And today people invent mountains of ad hoc heuristics to solve them. And instead, I've advocated for a very different way of going about it, where you specify what you want the cluster manager to do using a high-level declarative language like SQL. And then behind the scenes, you can have a compiler generate the code. You can do whatever you want. But turns out that separation actually unlocks a lot of potential in terms of flexibility and scalability. And we validated DCM across several use cases along these three axes on scalability, decision quality, and extensibility. And we have sufficient confidence that it works. It's an open source project. Yeah, if you're interested in building on it or extending it or using it, I'd be happy to follow up. So that's all. Thank you.
I have two quick questions, but I want to make sure that other people get to ask questions. Have other people go first. Sam.
I'm available after this as well. So if folks want to stick around and chat, I'm around. Yeah.
You mentioned that under the more heavily constrained model, there's more of a latency just in terms of overall data access that contributes to the end-to-end pod latency creation. And I can see how this works really well if there's like a single cluster manager for the overall cluster. If you were to have multiple cluster managers, obviously the maintenance of the database becomes more complicated as well. Would you see the same scalability, or is it that the cost of data access under more complicated database designs is still insignificant relative to the default scheduler?
So keep in mind that the database here does not need to be external, right? Like you can think of this as just a replacement for the in-memory cache of the actual cluster state. That's how we are using it, right? So this is not, so in Kubernetes, etcd is the centralized data store for the cluster state. And things like the scheduler basically subscribe to notifications from etcd and in their memory maintain some data structures representing this view, right? We are basically replacing that with an in-memory embedded relational database. But if you were to go into a model where you have the actual persistent store be shared, then I think it does raise some questions about, shared access, locking, concurrency, and so on, which, yeah, I haven't run into yet. So there, I know one hyperscaler, for example, who is considering replacing etcd with something like Apache Ignite. So that's supposed to be a distributed SQL-based database. I suppose they will run into these type of problems there, but yeah.
So Kubernetes, maybe I'll give some more color to the answer to your question based on that idea of a single place, namely etcd, where all the information is stored. If you were to go for a more sort of distributed scheduling approach where the knowledge about the cluster state is itself distributed, then you're in a very different world, because we now need these things in sync. They might disagree. You might only be able to make local decisions. So this is a centralized model, and that's, I think, what most serious large-scale schedulers have adopted.
Yeah, exactly. So there's always a shared state versus partition state question that shows up in those kind of settings.
Thank you.
Justus.
Yeah, so I'm basically wondering, this is kind of, this is like 3 questions kind of related. It's I'm wondering about the choice of SQL. So there's sort of 3 aspects of this that I find interesting. One is like what kind of, like, are you like supporting all of SQL, or like the reasonable core of SQL as we understand it?
I'm going to piggyback on that question because I wanted to ask how standard your SQL actually is, because some of the examples on your slides definitely contained additions to SQL, like maximize and constraint and things that don't exist in Postgres and MySQL.
Yeah. So the check and maximize clauses are non-standard, but the actual expressions are fairly standard, and it's a growing subset. We basically grow it according to needs, but for the most part, we are basically sticking with standard constraints. There are some aggregate functions that we support that we provide that are not common. For example, all different is one example of an aggregate function that we provide. But usually, yeah, other than the check maximize clauses, there's nothing new really. So it looks like standard SQL after that.
So in other words, when we talk about the database, this is actually something that you wrote, or at least where you wrote the SQL parsing part, right? Because extended, because clearly it needs to handle SQL that, if you just use SQLite or Postgres or something, wouldn't work. So your cluster database is not a standard relational database. It's a cluster.
Oh, it is. Hold on, it is. Yeah, so the database is like, we use H2, we've used SQLite, we've used Postgres. So that part is standard. The part to express constraints, which is very like only the DCM library sees that SQL, that part has this check and maximize clauses. But the database could be anything. We just need a JDBC connection to the database.
Interesting. Showed on the slide, there were some nested queries to like extract information from views and tables in the database. Those would be standard SQL queries.
Exactly.
And the extensions of the sort of outermost SQL that specify the constraints, and they go to DCM.
Yeah,
they don't go to the database.
Exactly. Yeah.
I have a related question. So is it explicit what query gets handed to the database and what query like DCM handles, or is that a thing that DCM decides to go like, oh, I'm going to take this sub expression, shove it into the database in like whole cloth?
Right now it is, but we are already sort of, there was another question, sorry, no. But right now it's the division is fairly explicit, right? Like these things go to the database, these things go to DCM. We're currently hitting a point where we actually want DCM to tell us what new views you want to add to the database that it'll use later. But like, yeah, that division is a bit annoying right now. But yeah, for now it's explicit. It doesn't need to be, is what I'm saying. Yeah.
In your slides, though, was that explicit difference highlighted in the examples in your slides? I remember sometimes there was a red check and that ended up turning into a constraint. But in the beginning with your first example, there was sort of an outer query and an inner query. There wasn't an explicit difference there. The outer query was for DCM and the nested one for the database, perhaps?
So in the slides, all of the ones that examples I showed you are DCM only kind of expressions. You can also write views that go only into DCM, and that basically triggers these intermediate variable constructions and so on, right? So usually anything related to manipulating variables or expressing constraints on them should be on the DCM side. Yeah. There's no reason we can't sort of have one gigantic schema with the constraints and we can automatically decide what goes where. But right now, this is the implementation. Yeah. There are good reasons to do it that way, because you can actually do some kind of constant propagation and things like this automatically if you wanted to. But yeah, we haven't gotten around to doing it yet.
All right, I think we should let people in the room run because they might have to get somewhere. I'll ask my question and then it looks like Justus has another, so I'll leave you guys to talk. I need to run because I have a meeting.
Yeah, I can go upstairs and hop on the
okay, you can do that. How about you do that while I ask Lalith my question? Okay, so there's this part where you compile down the code that you then put into Kubernetes, right? My understanding is that gets kind of generated from the constraints and the schema.
Yeah.
But what if I add a constraint? Do I have to recompile Kubernetes from scratch?
No. So the way the scheduler looks like, it's basically some Java code, right? And in there, we basically create the model. We compile it dynamically, basically at runtime. So, and that compilation is pretty fast. You will at least need to restart your scheduler. That's basically what will happen. But it's very, it would be very unusual for you to be able to sort of add a policy that quickly, because usually adding a policy means you're going to write a bit more code to get some more, I don't know, data into the database. There's going to be things of that nature to do. So it's, I think it'll be a bit hard to, on the fly, just throw in some SQL and have it still work, right? It assumes that you already have everything else you need in place, which is usually not the case. Yeah.
What language is the generated code in?
Right now it's Java.
And then you JIT compile and load that Java, dynamically link that Java code, bring it.
Yeah.
Okay.
Yeah. So we just invoke Java-C on the generated file. It's as simple as that. And then it takes care of whatever else it needs to. I'm really contemplating just interpreting at this point rather than, doing code generation. I just think it's just easier from a development perspective to make changes and yeah.
Okay, makes sense. Very cool stuff. Thank you, Lalith. I'll leave this open so people can continue chatting to you. I have to run to another meeting, but
thanks a lot, Malte. Yeah.